Okay. Let's start. And the video has begun. Okay. So, don't forget to sign in, girls. Hey, we are on Unit 10 Integration. This is the last and final unit. Please make sure that you take the big giant study guide over there so you can study whatever topics you still have trouble with on your way out. Okay. So, let's talk about integrals. Yes. We have a few different types of integrals. Here is. Oh. Yeah, I'm just fixing this right here. There we go. There we go. All right. So we have indefinite integrals.
That's not very nice.
Anybody know what an indefinite integral looks like? Tell me what kind of things it has and what kind of things it's missing.
Asymptote. No, is it a real thing?
An indefinite. No.
Oh, he has the open dots.
I can't talk to you with your tubes like
He has
that.
open dots.
An indefinite integral like this, you mean?
Oh,
Are you making fun of Jack?
No, it's incredible. Okay. And then we have a function here. Does an indefinite integral have any bounds?
he does.
No.
Oh, wait, no.
He doesn't have any
No, that's
bounds.
a definite.
And his answer will be a function.
But he has C.
Even more specifically, a family of functions where plus c takes on any value it needs to satisfy the initial conditions, okay?
That C guy is a people pleaser.
Wait, I was meant to. Do you know what CP is, Miss Wilczek?
I am not deleting this video because you have a problem.
No, because it's called Pac-On. It's called Pac-On.
See, Mikey's.
I mean, Ryan, Miss Wilczek, help.
You might deserve it. Okay, so now you can figure out, see if you are given initial conditions. Initial conditions could look like a point, or they could look like f of x equals y. So it could be a point, or it could be in function notation. Versus, what is the opposite of an indefinite integral? A definite integral. And he has bounds. What does your answer in a definite integral look like? It's a number, right? So you would get the original function evaluated at the upper limit minus the original function evaluated at the lower limit, and your answer will be a number with no c. And we have a few integration tools that we are familiar with. Remember, you don't know how to integrate products and quotients. So you might need to break up quotients as partial fractions, right? So let's say we have something that looks like this. I cannot break that up and write it like this. I cannot do that. But I can break up something that looks like this. X over x plus 1 over x. That's totally fine, okay? And the way you can remember is you can make a heart, but you can't make a whatever this would be. But you can't make a, sure, that is a beautiful representation of a fart, yes. So can't do that, but you can make a heart, okay? So integration tools. Good old algebra, that could be an example of good old algebra. Other more specific tools that we learned were U substitution. Actually, we should probably put a little note up here, a formal note. Don't. No. Product rule. When can you think of in particular when U substitution is very useful? when you have an integral and you have sine of x and sorry, and cosine of x. Why? Because their relationship is that one is the derivative of the other. So you let, even though he looks like a product and you're like, oh man, like I don't know, like a product rule in integration, you can use u substitution, and that makes it a very easy integral now, right? So if you see products, there's probably an easier way. So you let u equal, let du equal, and you rewrite the integral u du. Don't forget your du's. You guys forget them. You think they're optional. They are not. Put those du's and dx's in there, okay? When you have u substitution in a definite integral, what am I about to tell you? U substitution.
Oh, change the bound.
Yes. You must change the bounds. Okay. Let's give you an example. So let's say you have something that looks like this.
Alright,
And you let u equal, you let du equal. You have to do lower as a function of u, right? If you're putting everything else in terms of u, wouldn't that make sense where you kind of plug the 2 into your u substitution? Do you know what I mean by that?
Absolutely.
And then your upper is going to be your upper bound put in terms of the same substitution that u underwent. Okay. Let's see. What's another mathematical tool you guys remember for making integrals look easier to work with? What if you had something that looked like this? What would you do for that? Could you use u substitution there?
the GCF on the
No, you cannot pull.
outside. No, don't. Never mind.
You cannot do that. You cannot pull an x out of an integral. But you can do this, right? Then you get a nice little polynomial, and you just work piece by piece, right? So this is a method. This is a method. Okay?
So let's say instead of x on the outside, it was like, let's say 2. Could you then pull out the 2?
Oh, you can totally pull constants out. That's fine. I'm frozen, so. While I get unfrozen, why don't you guys try to think about kinematics? Yeah.
I can.
I simply cannot. You can pull out constants. Let's put that on there. Good. You can pull out constants. Let's say, for example, you had 4 sine x times 8 cosine x dx. You can take these, pull those out. Okay, good example. Okay, kinematics. If you have S, V, A, and you want to get from one to the next, you take the derivative. But what if you want to work backwards? Let's say you're given acceleration and you want to find the velocity. Ooh. You would integrate the acceleration curve to get the velocity curve. You would integrate the velocity curve to get to the position function. Okay. Okay, this thing is being very glitched today. What do I do? Oh, okay, great.
Nothing.
Do nothing. All right, let's talk about displacement versus total distance traveled. Do you guys feel like you have a good handle conceptually on the difference between the two?
Yeah.
So for displacement, I want you to think, how far from home are you on your trip? And then for total distance traveled, I want you to think the odometer on your car, right? So you could still be back at home, but it's going to tell you how far you went and everything. Out and
How
back.
do you spell
Odometer.
that? Yes.
I kind of mushed it all together so you couldn't tell, but I'm pretty sure it's Odometer.
Ah.
Okay. So with calculus, displacement is going to look like the velocity curve being integrated. You want to keep the negative areas negative, or keep the negatives negative. Because it's okay if the two cancel out. Your displacement could totally end up being 0. Just means you're back at the origin, right? Versus when you find total distance traveled, you need to take the absolute value of the velocity curve in order to account for all the backtracking and all the distance you went out but then came back, went out but then came back. Think your odometer, okay? So you need to make negative areas positive. What do I mean by make negative areas positive? So if you're looking at a curve, right, and you have like this, and you had an area below the curve, come on. What you're essentially doing is making it positive with the absolute value bars so you can add them together. Okay? I gotta blow my nose for a second here.
Oh, you took the pass? The pass.
She's still looking at.
One of my ninth graders gave it back to her on her own accord. I thought that was very responsible of her.
I mean, I guess. I actually
I was like, wow, okay.
I
Good for you.
completely forgot that I didn't take a pass, so I just like took somebody else's because I was the only one there.
I can't remember that
The great pass exchange.
very well. Let me tell you.
All right, so let's think about the cases where we have bounded areas. We kind of just touched upon it, but let's dig in deeper, okay? So when I have bounded areas, we could have areas bounded by the x-axis and the curve. So it could look like this. Areas bounded by the x-axis and a curve. You can think of the acronym SIT. And for the acronym SIT, oh, hey, color change. You're going to think sketch, find the points of intersection, and then T for take the integral. Okay? Yeah.
Go up a little bit, just a wee bit.
Take integral was too hard to write vertically, I guess. So, let's say you have a curve that looks kind of like, I don't know, like this. Okay. And you had to do it by hand. So you can't just type the absolute value of this guy into your calculator. You have to do it by hand, right? First you do your sketch so you can find your points of intersection. This guy is bounded by the x-axis and the curve, so you would find your points of intersection by finding what graphical feature corresponds to the points of intersection in this case? The zeros or the roots. Good job. So this is a negative area and this is a positive area. Stop being so painfully slow.
That's Stevie.
Wow, not to Stevie, to my computer. Shots fired. Okay, so I'm gonna go from negative, and now there's people at home. There is now a seagull in the room. So
That was Stevie.
Imagine if I watched this like
I'm just so
He's
confused.
poking you.
I'm still so confused how you.
oh God, what is this doing?
I know, yeah. Like I thought he would have been done by now.
This is like the only time I need this thing to work properly today, and it just won't.
Yeah.
Yeah. Okay, so now you set up the integral. Okay. Let's call this curve. Oh, Jack, do you have to go to the dentist?
Yeah, no.
Oh, good luck. What if he came back with a grill?
Yes, get a grill!
Yes. Oh no, he didn't hear our suggestion. Okay, so the area from -5 to 1 is positive, right? So we're going to leave him. What should we do with the negative area if we have to do this by hand?
Negative a bit.
We have to negate it to make it positive. Okay, that's going to give me my area there. I manually did it. I need to subtract negative areas. This is if I have to do it by hand. If I don't have to do it by hand, remember, how can I just write this in?
The absolute value.
Okay. What's the other type of bounded area problem we could have?
I don't know.
We can have an area between two curves.
Oh. That's your fault, Stevie.
Area between two curves. So step 1 is going to be the same as the other one. We're going to sit it out. Sit.
We're gonna
Sit.
what?
Sketch. Let's say this guy is g of x and this guy is f of x.
Lexi.
We sketch. We find the points of intersection.
He grabs you by the shirts.
Help.
Let's say this one is -2 and this one is 6. We use those points of intersection for our bounds of integration. And then we do top minus bottom. Do you need absolute value bars for a problem like this?
No.
Why?
Top minus bottom.
Yes, because it's always going to yield a positive value if you're doing the larger y outputs minus the smaller y outputs. Okay, so it's always going to be positive. You don't need to worry about absolute values and stuff like that.
I agree.
If the top and the bottom switch though, so if you get like this, and you have like it intersecting this line here, do you see how the top function and the bottom function switch? You have to split it up at the points of intersection, okay? If top and bottom switch, split up, integral by points of intersection. Do you know what I mean by that? I'd really like to get off this page because it's being very glitchy. All right, I think that's it for integrals. Let's do a problem that I thought was pretty summative and good, and then we can be done.
I think you know what? That was Stevie. Stevie can poop in his pants.
Stevie, you just ignore him, right? You just ignore him, right? Okay, good.
And normally he should do more. Look at my bag. It looks like Pinhead.
Wait, who is this? Wait, push it from.
Wow, you have a lot to print. What do you got to print in there, girl? Go ahead. Oh. Yeah, go ahead. You'll be able to catch up. This is easy, the beginning part. Okay, guys, so go to question number 10 for integrals. Oh, no. All my 9th graders do that. They, like, close the hole on the hood and then, like, sit in class, and they're like... We are given y equals x squared plus x to the 3/2, where x is greater than or equal to 0. Find dy dx. What are you finding? The derivative. Okay, easy peasy. I'm going to take the exponent down here, drop it. This is a clear inner function of x squared plus x embedded in an outer function of to the power of 3/2. Therefore, I'm going to use the chain rule to take the derivative. I drop the exponent down in the front. I reduce the power by 1. And then what do I have to do that most of you forget?
Times the inside.
Times the derivative of the inside. Okay. Let's see if we can kind of clean this up a little bit. 3/2 will stay out front. Let's move the 2x plus 1 into the front to be kind of a coefficient of this guy, which ends up being a square root. Okay? All right. Hence, find, and then we have the integral of pretty much the same thing we just found. What's the only difference, though? There's no 3/2 out front, so let's just see what we end up with, but I think they just wanted to help you kind of figure out what would be your u and your du, okay? So, let's set this guy up. We have an outer function of the square root, and then inside is x squared plus x. We also see that the derivative of x squared plus x, the inner function, is present in the original integral. Therefore, we should have an alarm going off in our head that this is going to be u substitution, okay? So we're going to let u equal the inside of the square root. I think a lot of you guys, when you were working through your problems today, you were like making the whole function. Like you were making the sine of 2x cubed the u. No, you want to do the inner function, and then the derivative crops up from there, okay? So we're going to let u be x squared plus x. His derivative is 2x plus 1 dx, yeah? And then we're going to set up our integral. We have u to the 1/2 power du. And then now, when I integrate, I'm going to add 1 to the power. And I get a new power of 3 over 2. Yeah, that's the same thing as multiplying by 2/3. Division by 3 over 2 is the same thing as multiplication by 2/3. So now I have 2/3. And then since this is an indefinite integral with u substitution, there are no bounds to change. I got to add a plus c, and I do have to put my answer back in terms of x's and not the u's. So I have 2/3 u to the 3 over 2 plus c. I got to get this back in terms of x's. So I've got 2/3 times the square root of x squared plus x to the 3rd plus c. That's that. That's that. Okay, so now consider the functions f of x equals 1/4 the square root of x squared plus x. Okay, that's f, and he's going to be this function down here. I'm just going to write it so I've got all my stuff visually written out. And then g of x is this curve, and he's going to be it's just not worth it to change the pen color, I think. I think that's what we're learning.
What are you talking about?
I saw.
Okay. Why do you think I labeled these?
So that you know what to subtract.
Yeah, so I know which function is the top and which is the bottom. Good job. It says the shaded region S is enclosed by the graph of f, the graph of g, the y-axis, and the line x equals 2. Remember, if there's a vertical line cutting off the shaded area, what does that equation of the vertical line become? One of the bounds of integration, right? So we're going to see this guy starts at 0 and he goes up to 2. Those are my bounds of integration. And then I'm going to set up the integral by doing top minus bottom. And I'm so glad I put them on the picture because now it's really obvious to see. It's going to be 5 minus x over 2 square root of x squared plus x minus 1/4 square root of x squared plus x dx. I just have to write down an expression. I don't have to do anything with this. I found it. Hallelujah. Let's move on.
Is this calc? No calc.
This is no calc. Yay for us. Are you guys okay?
Oh, please.
So, D says, that's okay. We've got this.
Yeah, we like to.
It says, hence, find the exact area of S. Okay. So, the exact area of S is going to come from us evaluating this guy up here, right? Don't get freaked out. What are our integral rules? We can break up integrals with pluses and minuses. They're just like polynomials, right? So if I wanted to, I could break this up as integral from 0 to 2 of 5 minus integral of the second thing minus integral of the third thing, right? But I do see that the x over 2 square root of x squared plus x and the minus 1/4 square root of x squared plus x share a common factor. And what is that common factor?
Square
Right. So I'm going to kind of put that on the back burner and not separate those two because I have a feeling I'm going to end up factoring that out in order to solve because I don't know how to do product rule, right? So I'm going to split it up so that way the 5 peels off so we don't have to worry about him anymore, okay? So let's split it up so we have 5. Don't forget your dx. You don't want to lose points for something silly like that. Minus, and then like what? Was that real? Like, okay. So then now we're going to keep the other stuff together because I have a feeling that we're going to end up using it as a GCF.
So like, since
But-
there's x's, you can't technically take it to the square root of x.
Right, but when we have u substitution,
Oh, yeah.
isn't there going to get like crop up an x from the inner function there, right? We just kind of looked at it when we did the derivative and we integrated. But also just be careful, right? I am subtracting the whole second piece. I'm factoring out a negative essentially. So inside my radical, I'm going to have the x over 2 square root of x squared plus x plus. Do you guys see why the sign changed there?
Yeah.
Okay. Okay. So then now let's get this one out of the way, right? When I integrate 5, I'm going to work piece by piece, right? When I integrate 5, what do I get? 5.
5x.
Yeah, and that's going to be from 0 to 2. Okay, let's just put that off to the side now, right? And then let's rewrite this guy so he has denominators, and then I'm going to get a common denominator. So instead of having them as fractions out front, let's get a common denominator, try to combine them, and see if that takes care of our problem, okay? So now I would have x square root of x squared plus x over 2 plus just plain old x squared plus x over 4 dx. And then I'm like, oh, I need a common denominator. Okay. Oh, silly you. Why did you try to change the color? Now we're going to be here for 9 years. Okay, forget it. Just forget it. The common denominator is what? 4. Okay. Oh, I'm starting to see a 2x. Are you starting to see the structure in this expression? Oh, I have a feeling I know where they're going here. Okay. So when I integrate 5, or when I evaluate 5 as upper minus lower, that's going to go up here, minus. And then now I've got 0 to 2 of 2x radical x squared plus x plus the square root of x squared plus x dx all over what? 4, right? We got a common denominator. Hey, what can we do with constants? We can pull them out front, right? Can't I put that 1/4 out front?
Sure.
Sure can. So now I got one, well, actually, let's evaluate the front. So what is that guy going to end up being? 10 minus 0 is going to be 10. So I have 10 minus. Let's put the 1/4 out front. And now I have from 0 to 2 of 2x radical x squared plus x plus the square root of x squared plus x. I got a common denominator so I could combine the two numerators. Okay, raise your hand when you see it. What's the move?
Put in the 2.
Hang on. What's the move?
In fact, GCF.
GCF of what?
X squared plus x.
Square root of x squared plus x. Good job.
So we don't really use substitution.
You are going to, but you don't, the U substitution is not clear at this stage.
I see it.
Yes!
I see it. Don't even play. Don't even play.
So I'm going to pull this out here. Oh, man. What do you know about 2x plus 1?
That's the derivative
That's-
of x squared plus x.
Well, that's on.
Oh, I see it now.
All right. So didn't we already integrate this, though? Like, do we have to use U substitution and change the bounds if we already know what this guy integrates to? No, right? I mean, you could if you want, just to make sure that you're doing it. But also, we want to know that, like, we can do stuff fast, right? So it's going to become that 2/3. And then we have the square root of x squared plus x. This guy ends up being to the what? What does this look like? Hang on. Oh, it's all to the 3rd power. Okay. Under the radical. And then we are evaluating this from what to what?
0 to 2,
0
0.
to 2, right? Yes. Okay. So now I've got 10 minus 1/4 and then all in crazy parentheses, I've got 2/3 times. And then let's evaluate upper minus lower. So I've got the square root of 2 squared plus 2, and then this whole thing's being cubed,
And this is no help.
minus, yeah, but like, look, the numbers will be okay. So I got 0 squared plus 0 to the third. Okay, so now what happens? I've got 10 minus 1/4. And then out here I've got 2/3. And then in here I've got, 4 plus 2 is 6. And then 6 to the third, but it's the square root of 6 to the third, right? So let's break out the square root of 6 to the third. That's going to be, yes, very good. So I've got 6 to the 2 over 2 times 6 to the 1/2. Yeah, is that not 6 to the 3 over 2? It is. What does this become? 6. What does this become? Radical 6. Okay? Or you could break it up like this. 6, 6, 6.
Whoa.
Multiply these together. You get 6.
Whoa.
And I just put a spell on you. Okay, so now we have 6 radical.
I need to get a 7 on this.
6, yeah. And this is, how many parentheses are there? My goodness. Okay, so then these are going to reduce, right? This becomes a 2. I now have 10 minus 1/6 times 6 rad 6. Do you see how it's not so bad? These go away. 10 minus rad 6. All right. Yes. Yes.
Dawn.